Okay, so we need to decide on, we need to combine these functions and also decide on the domain. And the thing to keep in mind is that the original functions that you're going to work with, those domains don't disappear. Those are the ones that we need to use. So for question number one here, we can look at that and we can say, okay, well this linear function has domain of all real numbers, while this quadratic function, this parabola, has a domain of all real numbers. So that means when I add these two functions together, their domain is still all reals because there was no limit. And of course, if they're telling me to, what if I subtract those two functions? Well, that will be, I mean, for this one, x squared minus, actually I've got that backwards, don't I? It should be, here. That should be, let's see, what is it? It's f, so 2x minus 1 minus x squared. And that domain will also be all reals. And then if we're multiplying them, that's just going to be x squared times 2x minus 1. And that domain will be all reals. Okay, I mean, yes, you could clean that up to 2x cubed minus x squared if you wanted to. So number one's pretty easy, and number two isn't hard, and number three starts bringing up some limits, but since that's an odd answer, odd number exercise, you have those answers. Let's take a look at number four. So for number four, I've got that square root function, and I know I can't take the square root of a negative number, but I can take the square root of 0, so x plus 5 has to be greater than or equal to 0, which means x has to be greater than or equal to negative 5. If I wanted to write that with interval notation, of course, it includes negative 5, and it goes to infinity. And so that's that domain. So there's a restriction on this domain. For the absolute value function, of course, that's just the absolute value function shifted left 3, and absolute value functions don't have any restriction on their domain. So this limiting domain is what's going to rule us in this problem. So again, to add those two functions, I'm just going to write x plus 5 plus the absolute value of x plus 3. And what's the domain going to be? Well, we said that there's this limit, and that's going to be the limiting domain. So I went out to Desmos.com, and I put this added function in. Notice the graph isn't being, there's no graph when x is less than negative 5. So that domain that where x has to be greater than or equal to negative 5 is even showing up in this graph, which is kind of cool. It's a way to check your work. So now for this question, let's look at number 6, because you have number 5. They want me to write the ratios of these two functions, so I'm dividing these two functions. And, I mean, maybe we could rationalize this, so this is f over g, right? We could rationalize that, but we don't have to for this situation. Now, what are some situations that are going on here? I know that I can't take the square root of a negative number, so x minus 2 has to be greater than or equal to 0, so x has to be greater than or equal to 2 is a restriction. And then I can't divide by 0, and I can't take the square root of a negative number, so for this denominator, the difference is I don't want to have an inclusive inequality, right? So in that case, I'm going to just subtract 4, so x has to be greater than negative 4. And since this is more restrictive, right? I mean, this function could include -3, -2, etc. But this holds it at 2. So the domain of this new function is going to be this, has to be greater than or equal to 2, and right, with interval notation, we're going to write from 2 to infinity and include 2. Okay, so the denominator didn't even come into play for this piece. And that's what you got to think about. Think about how the two pieces limited, and incorporate that limit, those restrictions into your new function. So for this number 12, we need to find these composite functions. This O notation, f of g of x, could be also written this way: f of g of 3 and g of f of -2. So that's just how you read that O notation. And one way to do it, since we could evaluate, we could generate the function. So for number 12, I could take, for the f of g of 3, I could say, okay, so I'm going to substitute in the g function into the f function. So all I did was I took that g function and dropped it into the x. Every place I saw an x in f, I rewrote it that way, and then I could clean it up. It wouldn't be wrong to clean it up. So this means, remember, when you have a binomial squared, you have to write it twice and FOIL it. So that's going to become 4x squared. What do we got? Minus 6x, and another minus 6x is minus 12x. And then -3 times -3 is positive 9, and then I'm going to subtract 1. So I'm going to get 8. And now I could drop in, so here's my f of g of x. And I could now evaluate f of g of 3. I could drop in 3 and say it's 4 times 9, because 3 times 3 is 9, minus 36, because 3 times -12, plus 8, and 4, of course, 4 times 9 is positive 36, minus 36 is 0, so plus 8. So this first part is equal to 8. And that certainly works. It's a lot of work, though. So the other way to do this is to find, let's now, we got f of g of 3. So what I could do is I could find g of 3 first. So I'm going to look at my g function. And g of 3 works out to be 2 times 3 minus 3, which is 6 minus 3, which is 3. And then I can drop that into the f function. What's f of 3? Well, f of 3 is going to be 3 squared minus 1, which is 9 minus 1, which is 8, which is what I just got doing it the other way. So to me, this way looks a lot easier than to find the function. But sometimes you need the function, and you have to do it that way. So hopefully that'll help you find the rest of these. So now they're asking us to find composite functions and then state the domain of each. So just like before, we have to be worried about the domain of the individual pieces. So for the I'm going to do number 17, since this has in it what I want you to think about. The domain of that parabola, that quadratic function, is all real, so that's not the problem. This g of x function, though, is that square root function, and from the work we did earlier here, we know that we can't take the square root of a negative number, so really what I'm saying is x plus 1 has to be greater than or equal to 0, so that means x has to be greater than or equal to -1, or if we think about it as an interval inclusive of -1 then to infinity. So that's going to be the problem with any domain we find of a composite function. So what are we going to get? We're going to get, so I'm going to find f of g of x, so that means I have to drop the g of x function into the f function, so x squared minus 1, and then I'm going to drop in the square root of x plus 1 into that. So when I square a square root, it cancels out because they're inverse operations, and -1 plus 1 minus 1 equals y equals x. So that is really what the composite function f of g of x looks like. That's what it is. However, that would have the domain of all reals, but we've got that original limitation from the square root function. That doesn't go away, so that's all we can use. So I went out to Desmos just to see, and as you can see here, we've just got the line. Actually, it's y equals negative x, isn't it? Did I make a mistake here? Oh, I think I did right here. Wasn't that supposed to be minus minus? Yes, that's what I did wrong. I should have written the square root of x plus 1 squared minus 2. You probably caught that. Minus 2. And there's the y equals negative 1. Y equals x minus 1. And if you look at that, it's a y-intercept of negative 1 and then a slope of 1. And this domain doesn't start until x equals negative 1. So when that original limitation is what we're seeing. So I hope that mistake I made didn't confuse you. You probably caught it anyways. But that's why we got to be concerned with the domain of a composite.